For starters, we're going to go from the basics. We always start with our sample, the thing that we want to analyze. That thing is going to go through an instrument, usually a spectroscopic instrument. That will be the examples that I will give in this presentation. And from that, you're going to obtain data. And this process has been done in instrumental analysis for a long time with a lot of different phenomenons. And with the progress in years, we have seen that even more data is being able to be collected. And thanks to that, also some instruments have become more accessible. So even more students can use them, even more personnel, and all of that, which is great. However, due to a lot of people now starting to use more instruments, they're going to face a little bit of roadblocks, some plateaus when they try to analyze their data. In this case, let's say that you're going to simulate a spectrum, or you look up how it looks in a reference or in a library, and when you take your measurement, it looks something like this. And you might say to yourself, what is happening? What am I doing with regards to the acquisition that's making it look so different, right? And this, it's something that's very common, right? When we do an analysis, we want a specific phenomenon to be seen in our results. However, nature is just going to be nature. A lot of phenomenons will start to collide with the ones that we want to see. And due to that, we will have, get my pen right here. Due to that, the data that you want to get, it's going to be the sum of two different things. What you want to see and what also happens. Okay, so this is something that's always going to happen when you try to acquire data from an instrument. And the things that also happen, sadly, is what we call artifacts. Okay, it's what we call artifacts. The artifacts are basically variations that you do not want in your spectra. Now, this depends on the context, right? Maybe you do want that specific phenomenon, but if your goal is to simply look at the spectra of a sample, you probably don't want this type of information on it. Now, there are three different types of artifacts. We're going to be discussing all three, starting with the baseline. Now, baseline is basically when some change happens to the background. Normally, you have a normal baseline for your spectra. This is one that you would simulate or you have in a reference. You may see that the baseline is basically where y equals 0, and it's fairly horizontal. But when you take a measurement, this happens. You might see that the spectra starts having a vertical offset. And this may happen due to instrumental effects or even luminescence. Another type of baseline effect is when it looks like a slope, like it was a vertical slope or a positive slope. In this case, it's also due to instrumental effects, but in specific, when this happens or it looks a little bit more curved, we usually chalk it up to what's known as fluorescence. However, fluorescence happens when the peaks in the spectra look a lot more smaller. So you might see something like this. This is probably a spectrum obtained that contained fluorescence, and fluorescence depends on the specific molecule, or maybe even impurities in your sample might have the fluorescence by themselves. So normally what we do with this is we do something called photobleaching, which helps us reduce the fluorescence, or we use certain data pre-processing methods, which we're going to see later. But these are basically the three different types of baseline offsets. You have a vertical, you have the slope, and the curved slope, right? So that's what we have for baseline. The second artifact is what we call scattering. And scattering is basically, this right here, scattering is basically when you have changes in the spectral intensity. Okay, so you have one spectra that looks like this, You have other spectra that looks like this, and then you have another one that looks like this. And you might say, what's the problem with that? Well, the problem is that all of this have the same concentration. All of this are 50%. And if you want to create a model that it's supposed to quantify or to discriminate between different spectra, you want them to be as consistent as possible. You want the samples to be representative. You want it to look something like this. All the ones that are in 50, they can vary, but you want it to vary at a smaller interval, right? And this is normally due to heterogeneity. Okay, heterogeneity in your samples and also by other instrumental effects. Normally, when we talk about heterogeneity, I'm not talking about a mixture where we have two different components that I can see clearly. That's called constitutional heterogeneity. What I'm talking about is the spatial heterogeneity or distributional heterogeneity. And what I mean by that is that the distance between molecules is different. They vary. They're not all of the molecules are not at the same distance from each other. They're varying their distances. And why is this relevant? Well, the relevant comes when you're trying to acquire data and you have a photon right here, and the photon is going to collide with the molecules and then go to the detector right here. Detector. So what's going to happen? The photon is going to collide with one of the molecules, and then it'll go to the detector, and that will give me the signal right here. And I can see a spectra very nicely. But what happens when the molecules start to move and they don't have the same spacing? Well, the photons are going to collide in a different manner. In this case, this photon in particular will collide with one of the molecules. It will absorb that energy. Then it will collide to another molecule. Then the molecule absorbs that energy, collides to another one, and then it goes to the detector. And since it collided with more molecules, the spectrum is going to have a higher intensity. However, both spectra had the same concentration. And this is a problem. However, it's a problem that can be identified by Beer's law, which is a law that dictates that the absorbance of a spectrum is dictated by the absorptivity, which is simply a constant, by the concentration, and the trajectory of the light. Normally, you have this one as a constant, you have this one as a constant, and let me put a con here so it doesn't confuse with concentration. Absorptivity and trajectory of light are constant, but the concentration is changing. That's what normally happens when you deal with Beer's law. But in this case, concentration is being kept as a constant, and the trajectory of light is the one that's varying. And that's what's causing the scattering. That's what causes that at different concentrations, you have such wide variations in intensity. Okay, so in addition to that, we have another type of artifact, which we call noise. And noise is basically when you see your spectrum and it has this fuzzy look like this. And it's really, it looks random, but it does have some sort of pattern. However, it looks a lot like static, right? Something like this. And the amount of noise depends on the instrument and the technique that's being used. If the technique is very sensitive, you're going to see more noise than with a conventional technique when you use an instrument. And with regards to noise, the main problem with it is that if you have small peaks, like the ones here, if the noise of your spectra is too big, you might not differ the two peaks from the noise itself. You might not see the peaks. You see them almost at the same level, so you basically even ignore that there would be the possibility of a peak being there. And this harms what's known as quantification and detection. You need the peak to be as clear as possible. If the peak is not clear, you cannot identify the molecule. Okay, so this is something that's really hard when you're trying to look at smaller concentrations. You might find them at big concentrations, but not at small ones. So in essence, if you have low noise, you can see even below of the normal amount of concentration that you can. And if you have a lot of noise, you're not going to see those lower levels. So what can we do to reduce these artifacts? The three that we saw already: baseline correction, legal baseline, scattering, and noise. What can we do to reduce these artifacts? What we can do is use something known as data preprocessing. And these are algorithms that are used where you can place a spectrum with unwanted variation, add it to the algorithm, and it will reduce that unwanted variation. It will not eliminate the variation all by itself. It will simply reduce it at a certain point. Normally, when you pre-process your data, it's a process that you're going to do after you acquire data and before you analyze it. Usually in that middle range, you might also pre-process data after you analyze. That could also be a possibility. However, it's normally placed in this specific area. And the main use or benefit of using pre-processing is that when you do a process of your experiment, which relies on designing, acquiring, analyzing, and then interpreting, if the interpreted results are not good enough, you're going to have to start all over again. And this is an iteration, right? You're going to be in a cycle. Pre-processing helps you have less amounts of iterations. Now, what can we do to reduce baseline, right? What we saw, you have the normal spectra, and then you can see it having a slope. What you can do is that you will, and let me change the color of my pointer, you can estimate the baseline of your spectra, and by doing so, now you will know specific values, and those values you can subtract them from your spectrum, resulting in a flat baseline. And that's exactly what we do right here. So here you have the estimated baseline as red. You subtract it, and you've been resulted with the spectrum with a y equals 0 baseline, which is what we want at the beginning. So this is a really great way to reduce baseline. You estimate it, and then you simply subtract it. There are two different methods that you can use for this. One of them is known as detrending, where you simply subtract a polynomial. So you use a polynomial to estimate the baseline of your spectra. And your polynomial can be simply x to the 3, or it can be a combination of different constants. So basically, you play with the polynomial in order to get the best results possible. Now, with asymmetric least square smoothing, what you do is you will create a polynomial as well. However, you will have weights. You will have weights that allow you to customize the curve even more. You can make the first part really flat and then go up, or you can go with an upward part and then a downward part and an upward part again. You can do a lot more with asymmetric least square smoothing since you have more variables to choose from. However, when it comes to creating models, I do not recommend you use data preprocessing methods that reduce baseline. I do not recommend data preprocessing methods that reduce baseline. Why is that? That is because each of the polynomials that you will determine will vary between spectrum. You will not have a unifying polynomial that will give you the best results for every spectrum. So for this specific case, this might be constituted as a lot and a lot of tampering with your data. It's simply too much tampering. What I would recommend is using this for aesthetic. If you want to simply show a spectra, then you can just say in the bottom, yeah, this was corrected with baseline correction, and you show the spectra just like it is. But do not use for model. Now, here's where you see asymmetric least squares in action. Here you have the spectra that's going to be transformed, and you have below the estimated polynomial for that specific spectra. After you subtract it, click here, you can see that now it has a y equals 0 horizontal line for the baseline, right? So here you have it with a curved baseline and here with a flat baseline. Now, derivatives are also a option when you want to reduce baseline shifts. And you have two specific derivatives that are really, really useful for this. And those are the first derivative, which is SG1, and the second order derivative, that is SG2. SG are the initials of the two scientists that created the algorithm, Savitzky and Golay. Now, what happens when you use derivatives? You have your spectra here. Let me get a different color. What happens is you get a certain amount of points, which is usually 1 point in the middle, 7 points at each side, for a total of 15 smoothing points. Usually that's the ballpark points that you usually use, right? I usually use 15 smoothing points. So you have the specific amount of points, and in that region, you will place a polynomial that mimics the spectrum. Then you go, move to the right, and you do the same thing. You get another polynomial that simulates the spectra. You do the same thing, rinse and repeat until you go through the entire spectrum. Once you do that, you can then, for each polynomial individually, you can calculate the derivative, and you will end up with a spectrum that looks like this. Now, the spectrum may look a little weird. However, basically, a peak will be represented as this. This part in the origin is going to be your peak. This is what happens when you use a first-order derivative. And one of the great things about the first-order derivative is that it eliminates vertical baseline offsets. The second-order derivative can eliminate vertical baseline, however, it's specialized on slopes, right? So if you have a slope spectra, as the one we saw below at the left, it will give you the same results, but the peaks will be downward. Okay, so it's a little bit more easy to interpret than the first order derivative because you'll have a spectra that's really similar, only that the peaks are below. So derivatives, they can reduce baseline shifts, and if you want to reduce baseline, I would recommend that you use derivatives. Do not estimate the line with a polynomial and then subtract it because it will change depending on your spectrum. For this, Savitzky-Golay, it's a general algorithm. It's an automated algorithm. You don't have to tweak with nothing. The only thing you have to add is which order derivative you want and how many smoothing points. That's it. And you can have the same thing for all of your spectrum. Another thing that the derivatives do is that if you have a big peak, usually big peaks are composed or built from individual vibrational modes. And if you do a second order derivative, you might see the peaks individually like this. So it helps to also see vibrational modes that were hidden previously. right, with your data. So I really like derivatives. I really recommend you use them if you want to reduce baseline and want to characterize your spectrum. Now, here are derivatives in action. Here we have a lot of spectra with a curved baseline. And when we apply derivatives, you can see that now it has the y equals 0 baseline and the peaks. In this case, since it is the first derivative, you're going to see your spectra like this. And that's the weird part here. But this center right here are the peaks of your spectra. So if you look back, here's the original spectra, and here is with derivatives. The downside to it is that it looks different, right? The spectra is going to look different. However, it will remain with the information that you want. Now, how do we reduce scattering? Right? Scattering being when you have different levels of intensity for the same sample. So what a lot of researchers found is that each spectra that you obtain with scattering can usually be described by a factor. Okay, so basically what I mean by this is you can take the initial spectra, the one that has the lowest value, and you can multiply it by different factors to obtain the other spectra. And if you do this, then you simply have to divide the spectra by its factor. I can put a 2 here. It's not a 2. It's 1. So you divide the spectra by its coefficient, its factor, and it will give you basically the same results as you would if you had the data corrected. Okay, so it would look like this. So you have this, you estimate the coefficients, and you get this. So this is what we do to reduce scattering. We determine what the factor is, and then we correct with it. Also, as a bonus, like this different variations in intensity, I literally multiply the spectra by these factors. These are literally what happened, right? The one that's blue, that's 1, I multiply by 2 to get the red one, and the 3 by 3 to get the green one. So it's literally what happened, and then I divided it, and I got back our spectrum. So there are 3 different algorithms you can use to reduce scattering. The first one, and the one that I use the most, is standard normal variate. What happens with standard normal variate is that you have your spectrum in this case, and the spectrum is composed of different points. Each point represents an intensity at a specific frequency. And what standard normal variate does is it takes only one point, subtracts the average intensity of all of the points of the spectrum, and then divides that by the standard deviation of all the points in the spectrum. And once it does that, you will get a new point that is corrected. And basically you rinse and repeat and go through all the spectrum and you obtain your corrected spectrum. So it's a really easy way to correct your spectrum. The best thing about this is that you simply do this one time on an Excel, you fix the position of the ranges, and you drag the values to calculate the others, and you're done, right? SNV is really useful, it's really reproducible, it's really easy. It's basically my favorite way to correct scattering. Now, robust normal variate, it's basically the same thing, but instead of subtracting the average, you're subtracting the median. All right, so it's really, really close to the same thing, only that you're using 2 different measurements for the center tendency of your data. Now, multiplicative scatter correction is completely different from standard and robust normal variate. You are reducing scattering, that's the thing that they have in common, but with multiplicative scatter correction, what you're doing is you're estimating a coefficient. You're estimating what coefficient you're going to divide the spectrum to then obtain the spectrum that's corrected. But you do that by using a regression, a linear regression. The y equals m times x plus b. If you solve for x, you get the equation you have right here. And these coefficients are the ones you estimate to then correct the spectrum. Now, this method is really good for giving results. However, for giving good results. However, the downside is that you need to tamper a bit, right? The method by default will use the average of your spectrum, of your spectra, to then correct the spectra. It will use the average of all of your spectra to correct the spectra. It does not go individually. It will get the average of all to then correct one. So if you have spectra from different things, you might get a different results. It might not do the work that you think it will. The extended version allows you to add a good spectra and a bad spectra, so it can even calculate the coefficients better than before. However, you need to manually insert them. It's a lot less reproducible than SNV, hence I prefer to use SNV. However, I do use MSC a lot when I do my models, but usually SNV takes the cake. Now, there are other types of normalizations that we do. Normally, the ones we use is one where the highest, or not the highest, the biggest area, we basically scale it to 1, and then the other peaks of your spectra will be proportional to that specific area that was the biggest. The other one is the maximum, where you have a specific peak that is the biggest of them all, and that's going to equal to a height of 1. And then the other peaks are proportional to that specific one. This in particular is one that's used a lot, but a lot in spectral analysis. Usually it's one of the first things you do. You normalize by the maximum. And the way you do this is by taking 1 point at a time of the intensities, as we did with SNV, and you subtract the minimum of the intensities for your spectrum. You subtract the minimum of the intensities of your spectrum. Then you divide that by the maximum minus the minimum. Once you do that, you will have your spectra going from 0 to 1, which is fairly useful. If you have multiple spectra, you basically let them you basically leave them in the same field, right? In the same playing field. It's going to look a lot better when you normalize for everyone. In this case, we have our scattered spectra, and we had the one here where we normalized. So you can see that the scattering gets reduced. However, it's not as good as SNV, but it's also pretty good. And it's usually the first thing that's done. This is one of the data pre-processing methods that is used the most. Now, here's a normalization in action. Here you have spectral with a lot of scattering, a lot of scattering. And here is the spectra when you apply the data pre-processing. So as you can see, you have a lot less scattering. And the good thing about normalization is that you still have, in an essence, the same spectra. It's not like with the derivatives where you have something like this, right? For the first derivative, or you will have something like this for the second derivative. You still maintain the shape of the original. Okay, so normalization is normally the best way or the best data pre-processing to use. Okay, so what do we do for noise? Well, for noise, we basically do the first part of the Savitzky-Golay algorithm. What we do is we take a specific number of smoothing points. In this case, there are 15, one in the middle, 7 by the left, and 7 by the right, and we estimate a polynomial for that specific range. Then we move to the other one, move to the other one, and so on and so forth until we go to the entire spectrum. And then you simply replace it. You replace the original spectrum with the one you estimated. Now, these are the two different algorithms we can use. Savitzky-Golay smoothing algorithm is basically what I showed before. You go range per range on your spectra, and then you simply simulate a new spectrum. Moving average, basically what it does is that it takes one point and it substitutes the point, that specific point, with the average of the points that are adjacent, the one that's on the right and one that's on the left. And by doing that, you will have less noise. And in effect, moving average is the best one to reduce noise. However, since you're averaging what you have at your sites, it's less effective for retaining the original shape of your spectrum because you're basically changing it. And when you do Savitzky-Golay, you're basically placing a polynomial that takes the shape. So it's a lot more effective at retaining the original shape, but it will reduce a lot less noise. Which one would I use? I would go with Savitzky-Golay. However, I will never, ever use smoothing algorithms when I make models. Okay, same as with the baseline correction models. I do not use noise reduction models when I do modeling. Noise reduction methods when I do modeling. Why? Because it's basically too much tampering for your data. It's not reproducible, or it's not even fair because you're basically cleaning it up for convenience. It's too convenient for what you want to do, and you're going to lose certain information. So I do not recommend using noise reduction methods. Now, here's a noise reduction method in action. Here you have a spectral with a lot of noise, and here you see it corrected. So it doesn't look that bad. It looks pretty similar, but I do not like it. I I really do not recommend you reducing the noise of your spectra. By this means, what you can actually do is you take multiple spectra, and then you simply average them. And since the noise has a fairly random pattern, right? It has a pattern, but it's fairly random. You can actually, when you sum all of the spectra, you will have ones that are negatives, ones that are positives, and they will cancel each other out. So I recommend you take a lot of measurements and then average them. Now, when it comes to real life data, or more like experimental data, the actual spectrum, the one that we have here in black, will be a combination of different artifacts. In this case, this spectrum has a bit of a baseline to it. It has a bit of noise. You can see the fuzziness on the spectra. And it also contains another type of artifact that I did not touch, which was cosmic rays. Cosmic rays are when you have these types of peaks where they are really, really, really thin. They are really weird. There are algorithms that are used to reduce them, to eliminate them. However, it's a bit more rare to obtain them. Mostly you will see them in Raman, and if that's the software usually eliminates the cosmic rays for you. At least the wire one that we have on our Renishaw in the laboratory, it does it for you. So, um, very important, actual spectrum is going to have a combination of different artifacts. So you have to remove them to have your ideal spectrum, which is the one in the bottom. Okay, so strategies with regards to data processing, pre-processing. Firstly, I would never use more than 3 different pre-processing methods at the same time, or more for the same data. I would not use more than 3. The common order and the common data preprocessing methods that people use is they correct baseline, they normalize, and then they remove noise. However, I do not like to correct baseline and I do not like to remove noise. So I typically normalize and call it a day. I use the maximum normalization where I go from 0 to 1, but then I can also use SNV to correct for a little bit of the scattering and a little bit of the baseline, but I will leave it there. I would stay with SNV and max, and I'm pretty happy with that. Now, the order does affect the results, right? It's not the same thing that you normalize your data and then you take a derivative, then you take a derivative, and then you normalize your data. It's not the same. The order does affect the results. Okay, so very importantly, strategies for data preprocessing. I use a maximum of 3 different data preprocessing methods for my data, and I place a specific order for them. You can play with it. You can like place one, then the other, and see which one gives the better results. However, have be very clear that the order does matter. It's really important and should be taken into consideration. Now, with a complex example, like the one I have right here, I have a lot of raw data, and I can see that the data has a bit of a curved sloped baseline. And I can see also that there's a lot of scattering on my data, right? There's a lot of variations in intensity. So 2 things that I can use is baseline correction to correct the slope, and then SNV to reduce the scattering. And when I do that, I can see the data on the right. It looks a lot more clearer. It almost has the y=0 slope, almost. And it's a lot better when you're going to analyze. Now, would I use the baseline correction? I would not. I would stay with the SNV and call it a day. But this is an example with a lot more complex data. Now, what are the programs that you can use to, in an essence, use data preprocessing methods? Well, you can use Python and R. These are 2 programming languages, which means that you need to learn how to program. That's the good part and the bad part. It's free, but you have to learn how to program. However, there are a couple of scripts available online so that you don't have to start literally from scratch. Scott Huffman, a professor, created this course in chemometrics in which it contains a couple of codes in Python. And from those codes, you can use baseline subtraction, derivatives, normalizations, a lot of stuff. So it's really, really good, right? So you have Scott Hoffman in his chemometrics website. Now, also our research group, CISAC, contains a web page called files/info for research. When you enter that web page, you can then select Python programming languages resources, and it will get you to this specific window. Here below is the URL to it. This specific window contains basically how to get started on Python. You will have all the modules that I usually use when I'm coding. And I've even created 3 different data preprocessing method algorithms from almost scratch, not really scratch, but I tried to create them in this way so that you can place multiple spectra and then get the results at the end. You have for SNV, you have for multiplicative scalar correction, and for Savitzky-Golay, smoothing and derivatives. The 3 that I usually use. Now, in addition to that, you can use R. There are a couple of scripts for R, specifically Antoine Stevens and Leonardo Ramirez Prospector package. This specific package contains Savitzky-Golay, SNV, and moving average. So it's really good. I recommend you search it if you're going to use R. Normally, the argument is that if you want to do statistics, R is more recommendable than Python. Python is a lot more general. However, if you just want to stay in statistics, R is a lot more friendly. In essence, the way you program in Excel, it's very similar to how you program in R. So if you know Excel, it's also a lot more easier to get to R. Anyways, another thing we have is the CCS CISAC webpage. I made another one, whereas in the same place, file/info for research, you go to our programming language resources. The link is right here. And in that page, you can also get started with R, shows you what to download. You can install all of these packages, which are the ones that I usually use. And you have two scripts on the from currently, I only have two scripts. One allows you to merge multiple .csv files in only one file, so you have all of your spectra when you get it out from the instrument. There are a lot of instruments that give you one file at a time. This helps you place everything on one file without spending a lot of time. The other one is to plot multiple spectra. If you have a lot of spectra and you want to plot it quickly with good quality, you can use this script right here. Okay, so other programs, these ones are not free. You have to pay. One of the most popular ones is Opus, in where you can use a lot of different data pre-processing algorithms. And it's really, really popular for spectral data. So Opus, it's not free, it does not require programming, and it's really good for data pre-processing. The other one is Origin Pro. Origin Pro is also really, really useful. It's used way more for plotting spectra and other types of data. You can also do certain types of analysis with Origin and also certain data pre-processing methods. It does not require programming. However, you can also program with Origin Pro in order to automate stuff. And I think that you can use Python or R. I'm not sure if both or just one, but you can also use that with Origin Pro. Now, the other programs that are not free are MATLAB and the Unscrambler X. MATLAB requires programming. However, if you pay for the PLS toolbox from Eigenvector Research, you do not have to program. You can use data pre-processing methods and chemometric models with PLS toolbox and MATLAB. In addition, Eigenvector Research also created a program called Solo, in where it's basically the PLS toolbox, but you do not need MATLAB to run it. So you only purchase Solo, and you can already use data pre-processing and chemometric models. And last but not least, the best program, and I'm being biased, is the Unscrambler X. I love this program. This is the best way I've had personally to use data pre-processing methods to create models. It's really user-friendly. However, it is really costly. It's really expensive. So if you have your proposal and you have some money you can spend, I recommend for the Unscrambler X. If you do not want to spend money for data pre-processing, then you're going to have to learn some coding, but the ways are still there. Currently, the Unscrambler has all of these different data pre-processing methods, and yes, it's really good. Now, here are my references. If you have any questions, you can ask me in the chat. You can ask me with your microphone. You can ask me in Spanish. I will also answer in Spanish if needed. And I thank you all for your attention, and I hope you all have a good day.